This video is going to be about statistics fundamentals in R. So for this one, we're going to need to look a little bit more closely at our data set. Again, this is a data set where we did a study at Fordham that tested whether people preferred advice from human experts or statistical algorithms when making predictions. And these predictions were about different subjects, and they had different time horizons, meaning they happened at different points in the future. So looking at our data, you see the first column is a participant ID, and the second column is called month, and this is how far into the future these questions were. The shorter questions were about things that would happen in September, and the longer questions were about things that would happen in November. There were two different domains, which were the subjects of the question. Some were about politics, and some were about economics. And then the RESP column at the very end, that is the dependent variable, and that ranged from 0 to 100, with low values indicating that people preferred advice from human experts and high values from machine algorithms. So it was a slider elicitation. So on the left was human, and on the right was machine, and the output from it was 0 to 100. So here's a little bit of another summary of what each variable was. There's also the stats CL variable, which is how many stats classes the participant has taken. But let's go ahead and start thinking about how we can analyze this data. Correlations in R can be called the core function. And then with the core function, you can enter two variables, and it will give you the correlation between the two variables. So here I called correlation on age and the number of stats classes people had taken. And you can see there's a slight negative correlation, but it's pretty close to 0. If you call the core function on several columns at once, as long as they're all numeric, it will give you a full correlation matrix. So here I called it on age, stats classes, and the RESP dependent variable. And again, these have to all be numeric variable types. If they are categorical or if they're strings, this will give you an error message. So as long as they're all numeric, you can do this and you can get your correlation matrix. There are some extra arguments that you can add to the correlation function. The method function, or the method argument, you can specify it as Kendall or Spearman. The default is Pearson. These are just different types of correlation you might want to look at. And then there's the use argument, which is applicable if there are missing values in your data. I encourage you to check the help page for the core function for more information on how to use it. If you want to check the significance of a correlation, specifically if you want to test the null hypothesis is equal to 0, you can call the core.test function. Here you see if we call that, here we're testing the correlation between age and their preference for advice. And here you see this test is significant by a t-test. It's significantly different from 0. We get a confidence interval, we get our t-statistic, degrees of freedom, p-value, and we get the correlation at the bottom. So next we're going to talk about t-tests. So the default, if you're calling the t-test function in R, is for a Welch's two-sample t-test. This is the test that does not assume that variances are equal across groups. If you want to use a traditional t-test that assumes equal variances, you could set the var.equal argument to true. And if you have a paired sample t-test, you could set the paired argument equal to true. So here we're going to look at an example, and again, we're going to look at our actual variable of interest, which is the RESP variable. And remember, high values for RESP means people preferred machine algorithm advice, and low values meant they preferred human expert advice. So what we want to do is test whether people's preferences were different depending on the domain of the question. So remember, this data is in long format. So that means that there is a column for RESP, and then there's also a column that defines which question or which subject the question is in. So we want to subset RESP for the two different question subjects. So we do that using the square brackets as we discussed in the indexing video. So we take a t-test for when RESP is domain equals economics and one for when domain equals politics. And this will give us our t-test. Here you see we get the t-statistic, the degrees of freedom, which are adjusted for the Welch's two-sample test. We get a p-value, which in this case is the smallest possible p-value R will report. We get a confidence interval of the mean differences, and then we get the mean of x, which is the first variable, and the mean of y. Next, we're going to look at ANOVA. So ANOVA is computed using the AOV function, but reported with the capital A ANOVA function. This is a little bit confusing in terms of what the different ANOVA functions do in R, but we'll explain a little bit about why and how each of them works and why they're so different. So again, we use the AOV function to actually compute the ANOVA. So here I'm creating a new ANOVA object, which I'm naming AOV1, and then I'm using the formula syntax with the AOV function to do an ANOVA of the dependent variable RESP on employee, which is participant's employment status. I just use that because it's an example of a categorical variable with more than one level. So this is, again, where it gets a little tricky. So in R, when we report ANOVA, we want to use the capital A ANOVA function, which is part of the CAR package. So you need to install the CAR package and load it to do this. The reason is the default little a ANOVA function only reports type 1 sums of squares. And in general, this isn't of interest to us. So we need to use the capital A ANOVA function from the CAR package. There's another wrinkle here. In R, the default contrasts are dummy coding or treatment coding. And R is actually parameterized in a slightly funky way where it will trip up the type 3 sums of squares if you're using dummy coding. So we need to change our default contrast before we use the capital A ANOVA function to get the correct type 3 sums of squares. And type 3 is what you'll usually see in things like SPSS and SAS. So if we want to compare to that, we want to get type 3 sums of squares. But to do it, we first have to set our contrasts to be orthogonal contrasts in the appropriate way. You can also get type 2 sums of squares, in which case this discussion about contrast doesn't matter. That'll be slightly different than what you get in SPSS or SAS, but it's usually acceptable to use type 2 sums of squares as well. So again, really important. First, you set options. You have to set your contrast with this options function. So you call options contrast equal control sum, control poly. There are different options for this. This one is fine. It's pretty standard. What this is doing is setting categorical contrast to effects coding and ordinal contrasts to orthogonal polynomials. We're not going to get into technical details about that. Just make sure that you do this before you call the capital A ANOVA function for type 3 sums of squares in ANOVA. Once we do that, we load up the CAR package. We call capital A ANOVA on AOV1, which remember that was the ANOVA object we created before. And we set the argument type equals 3 to make sure we're getting type 3 sums of squares. And this gives us our ANOVA table. In this case, employment is not significant. If we wanted to look at two-way ANOVA, we could expand the formula syntax with a plus sign. So in this case, our actual independent variables of interest are both domain and month. So here we have a two-way ANOVA without interaction. And then I again call the ANOVA function. And we see that domain is significant and month is not. If we wanted to include interaction, we could use the star sign for multiplication. And when we do this, we don't have to include the lower order terms. As you see, R will automatically include both the main effects of domain and month, as well as the interaction. If we want to test nested models, this is where the little a ANOVA function can be of use. So if you have two functions, one of which is nested within two models, one of which is nested within the other, you can use the little a ANOVA function, and that will give you an F test comparing the two models. And if you see our F value and P statistic are the same here as they were for the interaction above, because all we're really testing with these two nested models is a model with the interaction versus a model without the interaction. If we want to get the marginal means from our model, we can use the eMeans function from the eMeans package. So we load up eMeans, install it if you haven't already, and then you can create an eMeans object. So you specify the model as the first argument, and then the second argument is specs, and specs are the variable for which you're getting the marginal means across. So here we're getting the marginal means for domain. We see much higher values for economics, much lower values for politics. If you want to marginalize over the interaction, you include the by argument. So here we're marginalizing, we're getting marginal means for domain separated by month from our interaction model, and you see we get two separate sets of marginal means for each month. Now we're going to talk about regression and covariates. So regression is done with the LM function, and in R, ANOVA is actually computed with the regression method. I don't know if you remember from your intro to stats class, your regression class, you can actually do everything that you can with ANOVA just using multiple regression. And in R, the AOV function is actually a wrapper function for the LM function. So you could do everything with the LM function if you want. You don't have to use the AOV function unless it's more intuitive for you. So let's expand our two-way ANOVA to a regression with more variables, or in this case, I actually kept it as a one-way ANOVA. I should change that. So here we have RESP as predicted by domain with covariates for month and age. Oh no, I'm sorry, that is a two-way ANOVA. Confusing myself. Just no interaction. So our covariate here is age. And once again, we can call the big A ANOVA table to get our ANOVA table. And here you see we get an ANOVA table. And in this case, our covariate is significant as well, age. And if you want to get the full regression table, which includes all the coefficients, we can use the summary function. And that will give us a summary, all of the actual beta values and the R squared. And we're calling this on the LM object that we named previously. So here you see this is the output of the summary function. We get, for the estimate, we get the beta values, standard errors, standard errors, t-statistics, and p-values. And then at the bottom, we get our multiple R squared and adjusted R squared. And there's actually, it's cut off, but there is a significance test for the R squared as well.